There's still some space down here, so keep coming in. It's a privilege to welcome Achim Menges here to the University of Virginia. He is a professor and institute director at the Institute for Computational Design and Construction at the University of Stuttgart. And his work is best known for complex material system exploration, computational design, bio-inspired design, advanced fabrication and simulation. He completed his studies at the Architectural Association with Professor Michael Hensel, and has been producing amazing work at the University of Stuttgart for many years. If you don't know Achim Menges' work, let me tell you a little bit about the many ways you may have seen it. He has won over 30 awards, including from the Academy of Arts in Berlin, German Design Award, and a Wholesome Acknowledgement Award. He's been published in over 140 peer-reviewed publications and in 15 books. He's given over 200 invited keynote lectures, and his work has been exhibited in over 70 exhibitions. So if you don't know Achim's work, chances are you just don't know that you know it. We're very happy to have you here, and I can say personally, after admiring the work from a distance for many years, I'm very excited to kind of hear more about its development and the next steps that you're interested in taking, and how our students are going to be involved in that research. So thank you very much for coming.
Not sure whether, well, this one is working anyway, so we may not need that one. Yeah, thank you very much. I hope that was not the end of the presentation already, but yeah, thank you, Ayla, for the kind invitation, and Gina for the great introduction. I think it's a great privilege to present some of our work here this afternoon, and it's also a great privilege to teach here with this on during this fall term, and I'm absolutely sure that we're going to see some very exciting work, and I'm particularly happy that we have the chance at the very beginning of the semester now to go through together with all the students to some of the kind of preliminary investigations that we have done at the Stuttgart University. So maybe because it's a bit an unfamiliar context, I would just like to say that this is all work that is not done by just myself, but this is work that we do at the Institute, where we are about 20 full-time researchers working with me, but it's also a very interdisciplinary work where we usually collaborate with a lot of people from engineering, from natural science, so this is really taken to be considered. We also have the enormous privilege that we can use our research as a vehicle for sort of also exploring new pedagogical models. So we have sort of affiliated with or related to the Institute our own graduate program, which is called Integrative Technologies in Architectural Design Research, where we have about 50 graduate students with whom we can actually explore these things also on a kind of a student level. I think that's really important because it's very much, I think, the next generation of architects who will bring this work really to practice and to fruition. I think it's also important to say that this is equally an interdisciplinary undertaking. So in that program, we don't only have architectural students, but also students from engineering, students from computer science, students from natural science, all working together on eye level in one program and still receiving a full professional degree, which was the biggest problem in each discipline. So that's sort of the setting. That's important to bear in mind. So it's not a single man act. It's usually a really truly interdisciplinary collaborative effort. And in many ways, it's an effort that tries to embrace a very particular condition of architecture, which is, I think, a truly contemporary condition. Because why one can argue that the separation between the processes of design and making, which really have dominated architectural thinking since the Renaissance, is still largely intact in practice, one can already sense that a new understanding of the material is beginning to arise, where the material can actually be rediscovered through the computational. So in other words, computation enables us to engage aspects of the material world whose logic had previously remained ungraspable because they were lodged at too great a remove from the typical modalities of the designer's sense and intuition. And of course, let's say such a material-oriented approach is not without precedent. Actually, interestingly, particularly in the kind of history of German academics in the 20th century, you find some sort of interesting points to relate to. For example, Joseph Albers' material studies that he conducted at his forecourts at the Bauhaus in Dessau established quite an interesting precedent for the possible enrichment of design processes through what he called material experimentation. And it's quite important to note that Albers rejected established processes of materialization based on professional craft knowledge, so sort of the knowledge that is transferred by training, because he claimed that they stifle in innovation and invention. And instead, he identified the material behavior itself as a creative domain for developing new modes of construction and innovation. So it's really important to understand that his material studies, like the one that you see here, this is a bit a later image from the Black Mountain College already, but at the Bauhaus he did very similar things. That's not an architectural model as we know it. This is not a representation of an already established idea. This is actually the very origin point of getting an idea by working with and through the material. So another interesting precedent, which is very close to us and probably located at the other end of the spectrum, are Frei Otto's extensive series of experiments that he conducted at his institute at the University of Stuttgart. Through what he called form-finding methods, Otto investigated a vast number of different material systems in order to study their capacity to physically compute form. So I like to think of our work as trying to embrace both Albers' experimental approach of employing material as a driving force in a creative, open-ended process, and Otto's scientific rigor in conducting design research that investigates the formation of form and structure in both architecture and also in nature. Similarly, but located in today's context of computational design, simulation, and fabrication, we seek to explore the repositioning of the role of technology in architecture by primarily shifting from a mechanically to a biologically informed design paradigm that is really based on this idea of a synthesis of form, material, structure, and performance, which finds its conceptual roots primarily in the processes of becoming in nature, which we typically call morphogenesis, which is a process in which formation and materialization, very different to design, formation and materialization is inseparably and inherently related. So in summary, I may say at the kind of positioning of our work that this research really aims at exploring the notion of material-informed design computation and its manifold and deep interrelations with technology, biology, and of course culture. And as we try to pursue that not only as a kind of technical challenge, but also as an intellectual venture and an aesthetic exploration, we really try to seek to trace the emergence of a novel, what we like to call computational material culture in architecture. So I will now introduce three main areas of research focusing on materialization, material structure, and material performance through a small number of projects in a relatively detailed manner so that you get an understanding of the true nature of this work. Let me begin with the first field of research, which focuses on the relation of design and contemporary processes of materialization, which of course are digital and robotic. And the pertinent question in that research is how we can go beyond the current use of digital fabrication, which either leads to quite an exuberant exploration of freeform architecture or simply higher level of automation of building construction. So in contrast to that, we are interested in capturing the very specific affordances and constraints inherent to those digital fabrication environments so that we can take them as the point of departure for architecture inquiry and systematic design research. And as an example for that, I will show you one research project which culminated in the construction of a kind of research demonstrator building, which was an exhibition hall. At the heart of that project was the question how we can look at novel kinds of syntheses between what one could call one of the oldest construction materials that we have, which is wood, on the one hand, and the latest technologies for materialization, which of course is robotic fabrication. And it's interesting that if you basically bring these two things together, you can actually really innovate based on the affordances of those manufacturing possibilities. So for example, because the robot is a smart machine that allows that knows, that not only receives more numerical instruction, but knows that it needs to be precise and is able to compensate and achieve that in real time, we can actually produce very precise systems which allow to actually build without tolerances, which then allows for going back to almost craftsman's-like joints, which you can see here, those finger joints, which in the old days was only possible because the craftsman could compensate for tolerances in real time by basically the crafts processes. So we developed a novel timber blade system, which is a load-bearing structure. So it is the architectural and the structural system at once, which is based on those possibilities, but of course also faces some interesting challenges. So if you want to build something on an architectural scale, as you can see here on the right, from a system which basically is just a three-dimensional puzzle, you of course face the realities of physics, and that is that these kind of finger joints are of course very good in withstanding shear force at the edges. So if one blade wants to move this way, it's nicely held in place by these kind of finger joints. But if it's exposed to bending moments, it's not really good because it almost works like a pivot joint, and if it's exposed to tension, it doesn't work at all. So this is the moment where most sensible engineers would say this seems to be a bit of an academic exercise. But it's interesting that this is only the view from the perspective of within sort of the discipline of building technology. Luckily, we work with an engineer who has a broader scope and also with other people that informs his work, primarily actually people from natural science, because in nature you very often find precedent for concepts and principles that are actually beyond what we know from our own discipline. To substantiate that statement, we can look at this, which is a sand dollar that you may know. It's kind of sea urchin that you find here on the coast, actually along the entire east coast. And this is actually a load-bearing plate skeleton, which consists of polygonal plates. And if you zoom in a little bit on this plate edge, you will find that the plates of the sand dollar are connected by the biological equivalent to our robotically fabricated finger joints. So that in turn means that this natural system, the organism, has evolved ways of building a load-bearing shell as a plate skeleton in which all the forces on the edges are actually transferred into shear forces at the edges. So this is something we investigated together with specialists in biomechanics from the University of Tübingen. and we managed to identify the underlying principles that allow for this kind of performance. And then obviously the next interesting challenge is, how do you take those principles into a design process? Because of course they are not simple, they are actually difficult to comprehend. And for that, we, for a long time now, have sort of investigated alternative design processes and methods, in which also Essan's work has been instrumental, and one of those I will show you here. So we don't think of the design process as something where we model those kind of blades, or where we parametrically derive these blades, but we rather think that this is such a complex in a relationship that you want to have the blade find a spot where it complies with these biological principles and a whole lot of other things that I will show in a second, more or less by itself. So we think of the blade as an agent that exists in two spaces, the real design space and a kind of n-dimensional space that informs it about its various kind of parameters, which is too deep now to go into detail. But that includes, for example, an understanding of geometry. So you have to understand that if you want to build a shell like this, you have a dome-like situations where you get the polygons that you know from a soccer ball, but you also have saddle-shaped situations where you basically need to have these kind of bow tie shaped polygons in order to be able to build them from a plate of material, planar plate of wood. We have fabrication constraints, which we can simulate. We have constraints of the building code. These are all the buildings that I'm going to show you go through the full building permit procedure. They need to comply with the code. They need to comply with the proof engineer's demands. These are all things that we can actually inform the blade with, so that eventually we can all the blades run in that design environment, and they try to seek to comply with all those constraints. Now, what is really important is that this is a live design model, and you can interact with it as a designer. So it's not design automation. It's really a different way. So you can go in, you can hold a blade, you can shift it, you can arrange it, so you can take decisions from an architectural point of view, and the computer actually resolves the complex reciprocities that you're basically usually not really capable on integrating in the first instance. So I think it's an interesting example of how, let's say, designer and machine, human and machine, can interact together in new ways, and by that handle complexities that are usually beyond the scope of what we can grasp with our intuition. Of course, once the model is derived, we can basically just plug ourselves into the regular woodworking process. So most timber manufacturers in Germany have a machine like this. It's a so-called speed panel cutter. He churns out these plates in 2 minutes per plate, 3 minutes per plate, labels them, so they're all identified, and only then the robot comes into play and machines those highly precise finger joints. And because the robot can do all kinds of things at the same time, because it's a kind of universal machine, he also drills the pilot holes for the connections, etc., etc. He even does the quality insurance, which showed that this was another requirement by the proof engineer, that we have to monitor all the time the tolerances, that we get tolerances of less than half a millimeter, which of course is unheard of in timber and manufacturing, but more importantly, it is actually what allows one to build something like this. So in the end, the building structure is really a three-dimensional puzzle, does not need any particularly skilled labor, it does not need tools, anything on site. It can basically just be set up like a puzzle, and then in this case you can see how the load-bearing structure is the timber, and then some insulation, waterproofing, and all the stuff that you need in order turn it into a comprehensive building is added later on. And the final layer in this case was a plate of untreated large 3-ply wood, which closes the system. So on the outside, this is just a cladding, but on the inside, the bare structure is at the same time the architectural surface, which enhances, let's say, the spatial experience, not only by creating, let's say, an interesting contraction of the space where you have the transition zone from the foyer area to the main exhibition room, but also by leaving all these kind of 8,000 finger joints exposed, which create an interesting sort of play of shade on the surfaces. So in many ways, we thought that this is an interesting example how you can actually generate an architecture that is at the same time quite expressive, maybe also even evocative of the kind of principles, biological principles on which it's built, but is also very effective and efficient at the same time. So I think that's an interesting aspect, because nowadays we're very often made to sort of believe that you can either do something architecturally expressive, which means it's going to be somewhat exuberant, or you do something that is efficient and effective. And I think here, at least, we like to hope that we achieved both. It's efficient because we manage to build the entire shell, well, the entire building that you see here, which is the size of a kind of medium exhibition hall, which has a sort of volume of 605 cubic meters, with just 12 cubic meters of wood. And because we, from the beginning, set the design system up so that we can take all the offcuts of the strangely shaped panels as the hardwood floor, we didn't actually waste any of those materials. This kind of effectiveness is mainly due to the fact that it's a very, very effective structure. So you have to imagine that the entire span, which is 20 by 10 meters, is achieved with just 50 millimeter, that's about 2 inches, less than 2 inches, 50 millimeter thin primary load-bearing structure, which means that our shell, our timber shell, is proportionally about half the thickness of an eggshell, which gives you an idea that this is quite effective. Another thing that I think is particularly interesting is that one could also call this a truly regional piece of architecture, because all the materials that we actually use to build it, all the load-bearing timber structure, the fiberboard for the insulation, the boards, the panels for the cladding, are all sourced within a 200-kilometer radius, which I think is becoming increasingly important. And it's interesting that if we consider that our profession consumes by far the most, not our profession, but our discipline, the kind of industry that we intervene with, the building sector consumes by far the most resources on the planet, but we never care about where the things are coming from that we use. This will be sort of, I think, definitely something that we should pay more, or we will be paying more attention to in the future. So we are currently further pursuing this kind of research. 2019, we will build a shell that is 3 times the size, so it has about a 30-meter free span, and we'll still be able to do this with the same thickness of 50 millimeter, because we spaced those panels now, and we have a kind of hollow element that will be built and assembled actually fully automatically. So with the timber manufacturer that we work with, we are developing this robotic platform that does all the assembly of the plates, including the gluing, wood nailing, etc. I think it's also interesting to note that this is not just an academic investigation, but there's a lot of need for structures like that and a lot of possibilities. One is maybe exemplified by a project that we're currently doing, which is looking at inner city densification. So there's a lot of cities in Germany that really need to be further densified because property prices go through the roof, and it has become really socially exclusive to live in the city centers. So every square meter that you can gain is worth it. And with that particular lightweight system, we can actually extend already existing buildings. There's an example that we are just planning for construction in 2019, which is the extension of an existing parking lot on a typical bomb site in a German city. It's a kind of medieval city. There was a bomb site, so they built a big parking lot. And now that parking lot was from the 1960s, was already extended in 2003. And of that already extended building, we can now add another 2 floors, generate more than 1,200 square meters of space. And that's only possible because we have this incredibly lightweight system. It would be impossible to work with any other sort of architecture on the rooftop of that garage. I also have a little video to wake those of you up who have already fallen asleep with some heroic music, so I will not talk. So when we were working on this piece, and we basically actually in this case deployed plywood, we began to realize that wood is such a fantastic material because it's in the end is a kind of natural composite material that is made from cellulose fibers that are embedded in a kind of matrix of lignin and hemicellulose. And that sort of triggered an interest in saying, how can we sort of extend the scope of design by not just working with the given material, but actually designing the very material structure itself to achieve something that you find everywhere in nature, which is, in quotation marks, a kind of designed materiality. Actually, if you look at nature, it may come a bit as a surprise that if you consider all this incredible diversity of natural systems around us, that in the end, all biological load-bearing systems are fibrous composites. And it may even be a greater surprise to understand that nature only uses 4 very basic materials to achieve that. That's cellulose, as I just mentioned, which is the basic material in all plants. Chitin, which is the fibers in crustaceans and insects. Collagen in all the other remaining animals, including us. And then a bit of an exotic material is the silk that spiders, for example, use. And what is really also quite amazing is that those materials, the first 3, are not great materials from a property point of view. So the way what makes them really interesting is the way that nature arranges them in space. And that is at the heart of what all sort of load-bearing systems in nature make so successful. Now, what is also interesting is that these natural fibers, like the collagen fibers that you see here on the left, are on the fundamental level very, very similar to the synthetic fibers that we have now at our disposal, such as carbon fibers and glass fibers, which are, of course, the materials that have entered the canon of construction materials at the very last. And here we talk about 1930s for glass fiber and 1950s, 60s for carbon fiber. But we're still using them in a way that they're more like a replacement for other materials than trying to understand their fundamental principles. And that's because those materials are very counterintuitive for architects. Here you have a material that begins as something that is incredibly soft, basically a strand of carbon fiber. That's carbon fiber, a spool of carbon fiber. It's almost like silk. But once you actually cure it with resin, it becomes stronger and stiffer than steel. Actually, 5 times stronger than steel in relation to its weight. So you have to intellectually deal with that transition, and you also have to understand and that those materials challenge our understanding of construction because they're incredibly lightweight. 1 kilometer of material weighs 1 kilogram. And if you think about making sort of our discipline as a material practice, it is always based on very heavy materials. So how that affords a different way of thinking about the design process, but also a different way of thinking about an intervention on a site. I would like to show you another example, which is the Elytra Filament Pavilion that we built for the Victoria and Albert Museum in 2016. That was based on a competition that the Victoria and Albert Museum held for creating a kind of enclosure canopy for its central courtyard, which you see here, which is actually visited by about 4 million people a year. So the Victoria and Albert Museum is the 11th most visited museum in the world. In order to extend or intensify the use of the courtyard a bit, they were interested in generating a kind of semi-interior urban green space that would protect people from sun and, because it's Britain, more often from rain. So we won the competition with a proposal that allowed us to sort of have a very light footprint on the courtyard and showcase a kind of radical vision of what a kind of urban future green space could be within the kind of historical context of the Victorian Albert Museum, which was the sort of location of the first World Expo in 1851. So it's interesting that the door that is here on the very left is basically the arts and science store, which we thought is very fitting when you sort of approach that pavilion. What convinced the Victorian Albert Museum was that this was something that really looked at, let's say, the future as a kind of interdisciplinary, of kind of future construction as an interdisciplinary effort between architecture and engineering, which was based on a lot of research that we had done beforehand on looking into high performance natural composite systems, of which you see a very nice example here. So this is the elytron in the circle, which is the forewing, the hardened forewing of flying beetles, which is a natural composite that is made from protein fibers that are embedded in a, it's made from chitin fibers, it's embedded in a protein matrix. And that wing is primarily there to protect the fragile, transparent flying wings from getting crushed if the wing is actually crawling on the ground. So if we look at terrestrial beetles, ground beetles, this is a solid slab of material, as you can see here in the cross-section on the right. But for a flying beetle, it's a very intricate, super light, super strong, double-layered hollow shell. So we got the possibilities to look at it a bit more closely using this handy tool, which is a particle accelerator that our friends at the Karlsruhe Institute of Technology have, which is a sort of machine that has a 40-meter orbit, a 40-meter diameter, and you have particles flying around, and then you shoot them at our tiny beetle. And that allows you to basically generate a three-dimensional scan of that elytron with a resolution of 3 micron. So this is a computational model that makes us somewhat aware that computation technologies also build bridges and extend our sort of realm of inquiry to really levels of magnitude that were totally inaccessible beforehand. Of course, this is research that we again did with specialists in biomechanics. And if we then look at those shells, it's interesting, let's say from an architectural point of view, that the beetle managed to construct with this one system very, very different, let's say, spatial and construction situations, as we can see here. So on the top, you see a shell that basically spans between 2 support points. But then at the bottom, you have a shell that spans between a support point, rests on a kind of wall-like thing, and then sort of still establishes a huge cantilever. All things for which in architecture, we would decompose those elements and then actually use a very specific, let's say, tectonic structural solution for each one of them. The beetle manages to do all with one material system, and the secret of that system is revealed if you zoom a little bit further in, and this is that the beetle again does something very counterintuitive. If we would build a double-layered shell, we usually have an upper surface, lower surface, and we put some stuff in between. The beetle builds the whole thing from one and the same material, with all the fibers, as you can nicely see in this microscopic section, being continuous between the upper and the lower level. So it's really a let's say, continuous material system that is locally differentiated to respond to different requirements. So that principle is something we transferred into a building element that we can build with synthetic composites, where we have a glass fiber body onto which we wrap carbon fibers, which are all continuous between the upper and the lower side and can be laid in one sort of continuous go. And this is done with this kind of setup. So you have a very, very simple metal framework. The robot wraps the fibers around it. Once the fibers are there, you can actually take out the metal, folds together like an umbrella, and you can build the next one, and you can see a couple of those elements in the background. Now, I think what is interesting is that we managed to address 3 key issues for those kind of materials with that development. One is a more mundane technical issue that we actually right now hardly ever use these materials in construction because they require the enormous effort of building a huge mold. So our conception of these materials is that they're amorphic. That means they don't have their own shape, a bit like concrete. You cannot build with concrete. You need to build a foam work, and then you actually pour the concrete into it. In the same way we usually build, and this is a wind turbine blade, we build a huge form, then we lay the composite materials, fibers into that, and then basically the shape that we get is the superimposition of the mold onto the material. That is, on the one hand, economically problematic, but I think it's also intellectually not very elegant, especially if we look at concerns in, for example, fibrous sculpture or fibrous art, where there has been an effort to try to find out what is the genuine, let's say, articulation of those materials if you allow them to have a say in the kind of materialization process. So this is the wife of Joseph Albers, who said that, let thread be articulated again and find a form for themselves. That's more or less exactly what we do here. And by that, we also have the possibility to basically have a much higher level of control over where we want to place the fibers and where we basically situate them, locate the material, which I think is also important and interesting if we relate it to that quote, which is one of my favorite quotes, that in biology, material is expensive, but shape is cheap. As of today, the opposite was true in the case of technology and certainly in architecture. So I think here we can actually invert that, and because of new robotic fabrication technologies, we can really place the material only where we need it, and that's why we use very little of it. And through that process, we basically are able to identify the very self-expression of the material. That's probably more visible in this movie. So here you see the elements that we built for the pavilion. It's also obvious here that you cannot sort of separate between design, engineering, and fabrication. That needs to be a truly integrated process. And here now you can see how this works. So you have the glass fiber is the white transparent fibers, and the carbon fiber is the black fibers. They are laid onto this framework in a wet state. That means they're already saturated with resin, but still flexible. And then once they're on that framework, they find the form of the component basically by themselves, just through the interaction of fibers, and then they harden to form the elements. And with that actually simple process, we can build an infinite number of different elements, which ultimately are also equipped with this transparent polycarbonate sheet. We can also build these column-like structures by just replacing one of the edges with a stick. So that means that every element is finely tuned to its particular location within the structure, as you can see here. And of course, one of the drivers for that is the forces that the structure actually is exposed to. And that sort of results in a truly novel, I think, fibrous tectonic system that is not only, let's say, very expressive of the very material nature, but also incredibly lightweight. So you have 5 square meters of building element that weighs between 30 and 50 kilograms. So it's about 10 times lighter than any other system that we know. And this is interesting because it also allows us to think about other aspects that we usually take for granted. For example, we usually just assume that there's a strict delineation between the process of design, the process of making, and then the process of use in habitation. Now here we thought, because we have a building site that is only a couple of square meters, I mean, all you need in order to build this canopy is a bucket of resin, a spool of carbon fibers, so that's your two hands, and then the tiny robot, and with that you can basically build the entire canopy, which means that you can extend the process of construction and merge it with basically the lifetime of the canopy. So that's the idea behind the local production, which led to I think the idea that ultimately allowed us to win the competition was that we had a kind of canopy that had not a static configuration, but one that actually would slowly migrate through the courtyard, and by that sort of respond to the way it interacts with the users as a kind of dynamic space and evolving structure. So for this, we gathered information on how people actually respond to this, the space that is generated by the fibrous canopy, measuring the environmental conditions that are created, measuring how people interact with it, of course, in an anonymous state, and then having the pavilion reconfigure and extend and contract accordingly. One aspect that is a bit of a challenge in this context is that, of course, the VNA required a very stringent structural engineering report in order to get this built. So that was part of the 500-page contract that you need in order to intervene within a space that supposedly is surrounded by invaluable British cultural heritage. So you can imagine that if you show up and you say you're going to have a structure that walks around, that doesn't make the people particularly happy. So we convinced them by saying we can actually make the structure monitor itself, basically sense the forces in it, using the very same material, because glass fiber can also be used not only as the material that does the work, carries the loads, but also to actually sense the forces in it. So we equipped the whole structure with those kind of fiber optic sensors, so that we don't only have a predictive model, but we can actually really change the configurations on the fly, because we always know what the actual forces are in the system. And of course, that leads to quite a different understanding of, let's say, how agile a piece of architecture can be, especially if it has this kind of very minimal footprint on the courtyard, because, and that's important to stretch, is that everything that you see here is just fibrous materials. In the entire roof, there's not a single piece of steel. So only glass and carbon fiber, and that of course also leads to this very distinctive architectural appearance that picks up the light on the daytime, distributes it, because in the end it's sort of glass fiber, and at nighttime it inverts that situation where the fibers begin to glow when they're kind of flooded with artificial light, so that the pavilion becomes almost like a hovering cloud above the courtyard. So in many ways, I think this is an interesting example how you can really arrive at, let's say, alternative tectonic models if you engage with those technologies on a profound level. Currently, we're further exploring that, and we're building a much larger shell, which is going to have a 25-meter span, using a similar technique, but reducing the formwork even more. So this is in our lab currently. So you see these long, more rod-like elements that we built with this robotic system, where basically the element emerges in the void space between two really minimal tools. And we're very lucky that we can also see this already making its way into, let's say, private practice, currently designing a stage roof for a pier building in New York City, more or less directly in front of the Brooklyn Bridge, which is again a structure that could not be built in any other material because it's only possible to put it there because it ultimately weighs nothing. So to give you a small outlook of where this could go, we're also interested in seeing whether we can not also include, let's say, the building envelope and the entire sort of building process into that system by not requiring any formwork at all, but really by laying the fibers on the most minimal thing you can find, which of course is a kind of air bubble. So we were interested in basically inflating a balloon, a big balloon you can imagine, and then reinforcing that with carbon fibers until it turns into a stable structure, and by that becomes also a kind of novel piece of architecture. That was, again, quite a challenge, and we talked to aerospace engineers about it, and they said, no, don't bother. You cannot work with a non-elastic material, which carbon fiber is, and lay it onto something that wobbles around a lot, which, again, when looking at nature, you find organisms that have managed to do exactly this. This is a water spider. This is an underwater photography. So this water spider is interesting because it's an animal that lives underwater, but it needs oxygen to breathe. So what it does is it builds a kind of outer net that you can see here, and then it transports tiny air bubbles on its back underwater. They get caught in this sort of outer net, and in this way it inflates a larger air bubble, as you can see here. So it transports these air bubbles down, it inflates this larger air bubble, and then it ventures into the bubble and reinforces it from the inside with fibers, and then stays there because this is its kind of stable habitat. What allows the spider to do that is basically its kind of behavioral patterns that respond to the changes in the configuration in real time. So it's really a procedural, feedback-driven construction. And that's somehow what we also tried to do with this. So here you see the setup. You inflate a basically regular building-grade transparent ETFE membrane that forms a huge inflatable that relies on internal pressure. And then we glue the fibers onto that membrane. So at the beginning, the membrane supports the fibers, but at the end, the fibers support the membrane. Can you release the air pressure, and you're there with a kind of stable shell system. So for that, of course, their design process needs to incorporate both states, the fabrication state, the inflated state, and the final state, which is a compression state. So we map them into one design environment, and then we have kind of agent that walks through, sort of that navigates that environment, leaving a trace of fiber behind in a similar way that the spider does it. And the interesting thing about this is that this is not a design process only, but that becomes the control system for the actual fabrication process. That's what we like to call a cyber-physical system, which is not a term that we invented. This is starting to be commonplace in production technology. So this is indicating that there's no longer a separation between the digital and the material, but that these things become increasingly fused. And that's exactly what you have here. You have a design model. You gather information from the production environment, the tension, the membrane, where fibers already are, and then the robot makes decisions on the fly where to put the next fibers. So in many ways, while at the beginning the kind of layup process is steered towards the end, it is actually a bit of an emergent fiber structure. So it's an interesting, I think, starting point to contemplate what it means if design and making is starting to converge, and let's say formation and materialization are no longer thought of as strictly separate. So here you see the final moment of the production, where the robot is still working within the kind of pneumatic system. But eventually, a structurally stable state is reached so that the internal air pressure can be released and the pneumatic envelope changes into the pavilion skin by basically cutting out the openings. And what is left is, again, a very interesting sort of system that on the inside still exposes, let's say, the initial softness of the rowing bundles that remains tangible in the fibrous texture, but that, of course, strongly contrasts with the actually hardened state. So in a sense, that evokes at the same time a strong sense of transparency and even airiness, as well as quite a stringy leanness and tangible tautness of this extremely lightweight structure. It's also interesting that during daylight, there only remains a subtle trace of these fibrous structures on the reflective envelope from the outside, which of course transforms into quite an expressive texture when illuminated from within. So I think, again, the project shows how a higher level integration of design and making, which is enabled by those cyber-physical fabrication systems, allows synthesizing material performance and architectural performativity in ways that go far beyond a tried truth to materials that we know from sort of modernism and related fixed and singular structural and spatial topologies. Also have a little video about that project. So let me quickly finish with the last chapter, because I think this is the most also a very interesting one, and that talks about material performance. So it's very much a study of how we can use digital technologies in order to find sort of properties that have always been in the materials that we work with, but we haven't really discovered them yet. And one interesting example is if we go back to what we started the lecture with, supposedly one of the oldest construction materials that we have, and that is wood. And maybe you know that wood is what we call a hygroscopic material. So it's a material that actually absorbs moisture from the atmosphere, and when it does that, it swells. And if it sort of gives the moisture back to the atmosphere, it actually shrinks. Now we have about 4,000 years of craftsmanship that tries timber to avoid doing that, and we actually invest by far the biggest amount of energy in timber processing in trying to make timber stop doing this by basically kiln drying wood that you can see here, which consumes 71% of the energy in timber processing. So we thought, why don't we use that innate material capacity and we allow the timber to do what it wants to do, and that is to respond to environmental conditions over and over again. So about 10 years ago, we set out to design a fully responsive building envelope that changes with changes of the weather, but would not require any mechanical systems, any electricity, or any external energy. It would just be driven by the material itself. Now that sounds again a bit like a wacky idea, but we managed to implement that in this project for the Frag Center in Orléans, and we managed to do that by looking again at nature, where you find that this is commonplace. I'm sure you're familiar with plant cones. This is a spruce cone that grows on the tree, is in a sort of wet condition, then it falls off the tree. By that time it's already a dead plant organ, but it still manages to open entirely by itself without the need for any energy, just basically by responding to the environmental conditions. So in many ways, what the spruce cone manages to do is it translates that dimensional movement that we know as a big problem from wood into a shape change of its scales. And the fascinating thing, of course, is that this works always and is also totally free of any fatigue. So we managed over the years to understand that more closely and to establish a workflow that goes from scanning a piece of veneer and then basically working with it to the point where we can where we can actually create a choreography of really complex pieces, as you can see here. So this is actually one of those apertures that is only made from wood veneer and a composite, where the veneer is the smart part, that opens and closes with changes in relative humidity without the need for any electronics, any mechatronics, nothing. So here the material itself is the machine. And that allowed us to sort of conceive of an architectural envelope that at high relative humidity is closed, but once the relative humidity level drops, opens entirely by itself. That means on a sunny day, the pavilion is totally open, establishes direct relationships with its environment, but once a thunderstorm or a rain approaches, the relative humidity rises just by itself. That's a natural law, and the entire surface closes totally by itself. So this deep ecological embedding provides for quite a unique convergence of environmental and spatial experiences based only on this silent and subtle movement of the translucent veneer elements. So on a gloomy day, it actually turns into this almost chapel-like introvert space, whereas on a kind of sunny day, it opens entirely and creates this kind of direct visual and illuminative relationships with the outside. So this is something that we also keep working on by basically disintegrating the wood that we use for this project. Currently, we've sort of separated the cellulose from the lignin, and we print it together with the 3D printer, which allows us to actually have a more stable industrial process to achieve the same thing. So here you see the 3D printed samples on the left, responding to relative humidity changes, and the veneer composites on the right. And this is, of course, exciting because that means we can really, by structuring the material itself, by designing the material structure, we can not only create static systems, but we can actually create systems that are dynamic and respond to the environment. So I'd like to close with maybe two statements that are meant to be a bit provocative. Going back to this, I think for me, it's interesting to note that there's not any real innovation in that system from a technological level. So what you see here is a piece of wood, which has been around for a couple of million years. There is a simulation that is based on an equation that was established in the 1920s. There's fabrication processes that are from the 1970s, and still nobody had done that before. So I think the really decisive factor is not the technology, it's what we like to call computational design thinking that allows you to find those opportunities in even something as mundane as a piece of veneer. The second point that I want to make is that what I quite like about our studies is that they're all ultimately unfolding a very distinct yet quite different architectural language. So this is not about an architectural style, or this is not about a merely formal inquiry. I think it's a methodological inquiry that yields very interesting, I think, formal possibilities, which are sort of the next subject that we want to sort of investigate more closely. But I think it's important to understand that this is the product of the methodological research, not the sort of point of departure. With that, I would like to thank you for your attention.
We have about 15 minutes before we have to get Achim off to the airport this evening, so maybe we can open it up for questions.
What's your favorite project?
Sorry, can you?
What is your favorite project?
Is that Jeff Kipner's question that everyone needs to answer? My favorite project is the multi-hall in Mannheim by Frei Otto. Does it help you? Do you know that? You should check that out. It's a timber structure. What I find remarkable about that is that it's not only a radical design process in which Frei Otto really investigated, let's say, the form-finding method to an extreme, where you basically have your design, basically where you enter a relationship with the material almost like an accomplice in the design process. But he even took that to the level that it is the construction methodology at the same time. So the kind of exploration of how you generate a form and how you build it later on is more or less exactly the same. You should check that out. It's the only building that I know that was built from a flat grid of timber, basically a timber lattice, and it was pushed up to entirely by itself form an 80-meter wide, super intricate, in my eyes, absolutely amazing space, as I said, just by itself.
Yeah, Achim, thank you so much for, is this working?
Yeah.
For a phenomenal, really phenomenal and very inspiring lecture. Through many of your projects, you achieve sort of an alternative reading of materials, right, through computation and through sort of going against standards, right? And my question would be, sort of in the same way that you contest standards, at a certain level you can sort of push back and begin to change standards. So what has been your experience, for example, in doing this work, in going back to the standardization of materials and saying, well, let's rethink the material in terms of how it's mass produced to be able to exercise change at even larger scales?
I mean, that's a really relevant and important question, of course, because in the end, this aim for standardization is something that hasn't been there forever. I mean, this is basically the side product of industrialization. So, and I think particularly when we talk about timber, and that's also a little bit what the studio is about. Beforehand, I think there was a greater understanding of the subtlety of timber, which of course every piece is different because it's not produced as a construction material, but it's grown as a functional tissue of a tree. And we lost that because industrialization meant standardization, meant that we don't refer to wood even as wood anymore, but just as a kind of geometric entity, which is obviously particularly striking here in the US, where you would say it's 2x2, 2x4, so it's not even a piece, you don't even identify it anymore. It's a kind of geometric container that is filled with some stuff. And of course that digging just a little bit deeper and understanding that there is an anatomy of the piece of wood, and that affords a lot of possibilities that we usually refer to as problems, opens up a dramatic scope for architectural inquiry, but also for questioning our standards. I mean, the reality is that because we don't understand wood, we assign a safety factor of 2 to it, but we understand steel, so it comes with a safety factor of 1. So everything we're going to do with timber is going to be twice as wasteful just because we basically don't know how to handle it properly. And I think that's something where I think we can overcome with digital technologies. This may be a mundane example, but we can overcome exactly those kind of standardization, which is really not aligned with the possibilities that we have now. I mean, every piece of wood that is sawn in a sawmill nowadays is scanned, because the sawmill tries to maximize profit, so they try to figure out where the knots are and the defects are. So once the thing is actually processed, you have a comprehensive data set of the piece of wood. But once it's on the truck leaving the sawmill, all this is lost. Because ultimately also architects don't tap into that reservoir of possibilities. So I think there's a lot of those aspects that even in the most mundane balloon frame building could allow you to challenge established ways of doing things and question preconceptions. And that's what it's really about, no? That's also, I think, the reason why we like to look into biology, because it makes us question the preconceptions of our own discipline and allows us for, let's say, out-of-the-box thinking.
Hi, thank you again. That's a really amazing, super inspiring talk. Just following on that question, it made me think in some ways this sort of lack of Cartesian geometries. And isn't it the most efficient system is to use, for example, the standard 2x4? Though I love the inventiveness, particularly in the last project talking just about the properties of water or moisture and how that can change the expansion or the properties of wood. But does your work preclude the idea that Cartesian geometries will ever be a smart way of building?
No. I think this is pretty Cartesian because it's a flat slab that is just a little bit inclined to create that geometry, to create that sort of gesture of opening up the V&A pavilion. It's kind of, but I get what you're saying. I understand that.
Because I think you're provoking with your work, but I also think in some ways like.
No, I think that's it's relevant. And I think honestly that's exactly the next step. I think we because in Stuttgart we have a certain soft spot for shells and membranes. That's what we engage with, and there's a good reason for that. But we, for example, made a study about timber panel structures. And how the arrangement of the, let's say, 2x4 sticks in the panel, you could actually, by not doing that in a regular fashion, but in a way that every craftsman would cry about, you can actually save 25% of the material It's just that it's complicated to build. And of course, if that complexity is taken out by a different mode of actually manufacturing, then it allows you to actually tap into that. So it's not that we want to exclude that. It is just that I would say in a lot of those studies, you arrive at shell structures sort of more or less automatically, because in the end there's nothing that rivals them unless you want to go into multi-story construction, which is something you want to do.
Thank you, Achim. Really fantastic work. We were a little bit talking when you were talking about, that basically nature creates tension structures, etc., only by using 4 different materials. And then everything is extremely lightweight, and then everything is somehow built through a robot. And do you see your main application maybe at the end of the day, not necessarily on the planet, but somewhere else out in space, where exactly these conditions are super important and crucial?
I think what we have to face as a profession is that these conditions are super important on our planet.
Okay.
Because the building industry produces 40 to 60%, sort of consumes 40 to 60% of the energy and resources on our planet, depending on what study you believe. UN says 50%. It produces 50% of the waste. Construction of new buildings produces per year 5 times more CO2 than all the global air traffic. I think it's really at the time that we have to radically rethink the way we construct buildings, especially if you consider that that's another UN prediction that we have to build another 230 billion square meters of floor area in the next 35 years. I mean, if we do that in the way we build now, we will not have a planet anymore to venture somewhere else. And that's the fact. And I think that's why, I think that's not the primary driver, but in the end, it comes down to that we need to look for alternative models of construction. Whether this is a possibility or not, this is meant to be a modest contribution in that alternative thinking, but we will have to, because the way we do it now will just not work out. And one day, the day that CO2 emission of construction materials will be taxed in the same way that the CO2 emission of personal transport is taxed, I mean, we will all have no clue what to do next. No? And I think that day has to come.
It has to come.
So I think it's, I would say, especially for work on this planet, it is really relevant to work with lightweight, minimal impact materials.
So I'm assuming that you are working a lot in the scale of the pavilion, that the pavilion is a kind of lab situation. Is your next ambition to go multi-story, to extend the scale?
I think on the one hand, we are interested in multi-story construction, and we are looking into this actually already now. On the other hand, I think the main outcome of what I present here is not, let's say, a carbon fiber construction system or a timber blade shell. It's, I think, a different way of design thinking. And that's also what we try to basically communicate to the students with whom we build these things. No? I think I also need to say that all the things that you saw, the robots, the effectors, the tools, this is all done by designers in order to show them that digital technologies allow you to radically expand your understanding of what design is. You can design the materials, you can design the processes, and what you really require is a certain, let's say, eagerness and ambition to do that and to exploit those opportunities. So I think what I'm trying to say is the main outcome, I think, is that. This is also what I would be confident that this will hopefully make a contribution to our discipline. Whether this does, we'll see.
Thank you, Achim, for this amazing set of examples. I think it's really interesting the way that you're kind of probing this responsiveness over time and lack of predictability, particularly with the last project where you start to embed a kind of performance in the material that is going to respond to its environment in a way that's maybe starting to push at this idea of a tightly controlled environment. And my question is maybe a simple one. I'm very curious about what's happening under the ground in all of these. This is where the kind of predictability of the prefabrication meets the lack of control and maybe the difficulty of these lightweight structures and kind of anchoring them. How much has that proven a challenge with some of these?
That's an interesting question, because I think that's the typical Frei-Otto conundrum. But I think what we have here, with all the research pavilions, what you see is what you have. Because under the space where we put the pavilions, there's an auditorium, so we're not allowed to touch the ground. And that's sometimes a challenge. The one pavilion that I showed you, the water spider pavilion, the whole weight of the entire thing was 260 kilograms. But the force at the tip, the pull-up wind force, is 7 tons, which this structure needs to withstand. So actually, self-weight is not an issue at all. Here, for example, in the Victorian Art Museum, we were not allowed to insert anything bigger than an earth anchor, which is about that long and has a diameter like this. And this is how all these columns are actually secured. So because we don't actually have any pushing force on the ground, the only thing that could happen with this thing is, again, that it flies away. And that's something you can nicely, again, I think one of those columns here has 4 tons of uplift, each one. And that's something you can actually accommodate with a very lightweight intervention in the ground as well.
And with the wood, was the settlement an issue at that level of precision, the timber shell?
That's something we actually monitored. So we keep on going back and scanning the piece. And the nice thing about these finger joints is that if the wood slightly sort of warps, it actually tightens the connection. So that was assumed to be a big problem, but it turned out to be not a problem.
Hi there. Thank you for your talk. I'm a cyrophysical systems engineer, and I'm really blown away by how inventive some of this work is. And I've showed at least one of the pavilions to other engineers, and they felt the same way. I was just wondering if you had any advice to offer or musings to share about how we can further encourage architects and engineers to work together to continue to find these little details and work them into full structures.
I think honestly, for me, there are two answers to that question. We work a lot with engineers, production engineers, system engineers, and I think the way to work with them is that it's a kind of you work with them in situations where everyone has an insight. Everyone has a gain in that collaboration. I think very often that actually applies for everything. It's not just engineers, but it's also biologists. They don't like to work with architects and just deliver them some ideas. They also want to do their own sort of scientific work, and that means they need to generate insights that are relevant for their discipline. And I think in Germany, at least, if you want to get funding, that's a given. So you need to make sure that it contributes to any of the involved disciplines. And I think it's also a very good way of working together, because that means that you're also taking each other serious. When it comes to the first question, how we can motivate more of that, I think that's, in the end, it's a kind of educational issue. That's why we have the program that I showed you at the beginning, where we have mechanical engineers in the program where they can experience firsthand that it's sort of enriching their own sort of way of doing, sort of enriching their own sort of work if they work together with other disciplines from the beginning on eye level. And I think that's sometimes, especially for the engineers, is also very, very interesting, because here, cyber-physical systems in production engineering are meant there ultimately to compensate for problems in the manufacturing workflow. So you basically measure everything, and then you do matchmaking with sort of the lowest tolerances and but there's not really a vision what that could do as a new thing, no? And I think that's what I think a lot of those. That's where it's interesting to work with designers, because that's what sometimes that they like to engage with. So I think there's a lot to gain from both sides, and I can only encourage that sort of interdisciplinary work.
Maybe I could ask one last question, and then we have to ship you off. And I just want to say, Achim will be here 2 more times this semester, so you have plenty of time to think about the questions that you have and take advantage of his being a visiting professor. So, sort of two questions. The first is, and this goes back to Felipe's original question, in asking about sort of the relationship between form and material, because at some moment when you're studying the wing of a beetle, you are dealing with material properties, but you get to a point where you're analyzing it formally, but at a microscopic level. And so I guess, what's interesting to me is it starts to establish an understanding of this continuum between form and material in relation to scale. So how has that affected your thinking about that relationship sort of over time?
Of course, I think the interesting thing, but when you start to look into nature, is that there's no you cannot differentiate between material, structure, and form.
Yeah.
That's integrated, and no biologist would ever even think of doing that, whereas we tend to sort of nicely disentangle that. I think what I find interesting about that inquiry, and also the history of it, going back to people like Albers, Otto, Candela, you name them, is that is almost a little bit an alternative history to, let's say, a material-oriented design approach, where, of course, that discourse has a bit been hijacked by the sort of material idealism, which is about the truth to materials, the Louis Kahn thing about asking a brick what he wants it to be. And if you really, if it comes down to it, it's a really questioning that situation. Because what happens in most of these situations, I think in the end, any architect would claim that he sort of designs in a material-aware way. But in most instances, that means that you superimpose a known typology onto the material, because that's the way you do it. That's the textbook knowledge of how you do masonry walls, how you do timber structures. And I think the interesting thing is that there's an alternative to that, and that has a kind of lineage in our own field, but it also, and not without incident, sort of those people that were interested in that alternative way of looking at materials very often refer to nature, because there you can find those let's say, preconceptions challenged a lot.
Can I ask you one last question, which then we'll relieve you? Maybe, given all of your research and all of your work, how do you think now about architectural education? How has that changed your idea of the way in which we should be educating architects?
Okay, that's how many hours do we still have? But that's of course it's difficult to give an immediate answer to that. But I think let's say the short version is that I think it's really on us in education to make that change, because what is becoming increasingly worrying for me is that I see that a lot of the, let's say, boundaries, limits, thresholds that are basically the problems that we face when we want to engage with something like this are things that our profession actually has built up in its institutional bodies, in its frameworks, in its legislation. So I think we are kind of on the verge a little bit, as I think it would be our role in society to be progressive and explorative. But then we have set all these protective mechanisms in place. As I said, that relates to the education system in the same way that it relates to, and that is accreditation, all these things, as it relates to the legislative framework in which you need to operate as practitioners. all these things. And I think that's really a problem. So I think the socio-cultural barriers are by far more profound than any of the technical issues that we discussed